Greeting respected sir and viewers. Today I Wave Sarin gonna represent before you on the topic wave propagation in optical fiber. An optical fiber is a flexible transparent fiber made by silica or plastic to a diameter slightly thicker than that of a human hair. Optical fibers are used most often as a means of transmission between two ends of a fiber and find wide usage in fiber optic communication, where they permit long distance communication without a loss of data. Fibers are thus used instead of metal wires for signal travel along electric. Fibers are also used for illumination and imaging and are often wrapped in bundles so that they may be used to carry light into or images out of confined spaces, as in case of fiber scope. Specially designed fibers are also used for a variety of other applications, some of them being fiber optic sensors and fiber lasers. Optical fibers typically include a core surrounded by a transparent cladding material with a lower refractive index. Light is kept in the core by the phenomena of total internal refraction, which causes the fiber to act as a waveguide. Fibers that support many propagation paths or transverse modes are called multimode fibers, while those that support a single mode are called single mode fibers. Multimode fibers generally have a wider core diameter and are used for short distance communication links for the applications where high power must be transmitted. Single mode fibers are used for most communication links longer than 1000 meters or 3300 feet. The boundary between the core and cladding may be either abrupt, as in case of single index fiber, or gradual in gradient index fiber. Light can be fed into optical fibers by using lasers or LEDs. Fiber is immune to electrical interference. There is no crosstalk between signals in different cables and no pickup of environmental noise. Information travels inside the optical fiber is even immune to electromagnetic pulses generated by nuclear devices. Fiber cables do not conduct electricity, which makes fiber useful for protecting communication equipment in high voltage environment, such as a power station, or metal communication structures that are prone to lightning strikes. The electrical isolation also prevents problems with ground loops because there is no electricity in an optical cable that could potentially generate sparks. They can be used in environments where explosive fumes are present. Wiretapping is more difficult as compared to electrical components. Index of refraction. The index of refraction is a way of measuring the speed of light in a material. Light travels faster in vacuum, such as in outer space. The speed of light in a vacuum is about 3 lakh kilometers per second. The refractive index of a medium is calculated by dividing the speed of light in vacuum by that to the speed of light in the particular medium. The refractive index of a vacuum is therefore 1 by definition. A typical single modem fiber uses for telecommunication has a cladding made by pure silica with the index of refraction about 1.44 at 1500 nanometer and a core of doped silica with an index around 1.45. The larger the index of refraction, the slower light travels in that medium. From this information, A simple rule of thumb is that a signal using optical fiber for communication will travel at around 2 lakh kilometers per second. To put it another way, the signal will take 5 milliseconds to travel 1000 kilometers in fiber. Thus, a phone call carried by fiber between Sydney and New York, a 1600-kilometer distance, means that there is a minimum delay of 80 milliseconds between when one caller speaks to another one hears. The fiber in this case will probably travel a longer route, and there will be additional delays due to communication equipment switching and the process of encoding and decoding the voice into and onto the fiber. Most modern optical fiber is weakly guided, meaning that the difference in refractive index between the core and cladding is very small, typically less than 1%. Now, total internal reflection. When light traveling in an optically dense medium hits a boundary at a steep angle larger than the critical angle of the boundary, the light is completely reflected. This is called total internal reflection. This effect is used in optical fibers to confine light in the core. Light travels through the fiber core, bouncing back and forth off the boundary between the core and cladding. Because the light must strike the boundary with an angle greater than the critical angle, only light that enters the fiber within a certain range of angles can travel down the fiber without leaking out. This range of angle is called the acceptance cone or acceptance angle of the fiber. The size of this acceptance angle is a function of refractive index difference between the fiber core and cladding. In simple terms, there is a maximum angle from the fiber axis at which light may enter the fiber so that it will propagate or travel in the core of the fiber. The sign of this maximum angle is the numerical aperture or NA of the fiber. Fiber with a larger Na requires less precision to splice or work with than fiber with a smaller Na. Single-mode fiber has a smaller Na as compared to multimode fibers. Graded index fibers or multimode fibers. Fiber with a larger core diameter than 10 micrometers may be analyzed by geometrical optics. Such fiber is called multimode fiber. From the electromagnetic analysis, in a step index multimode fiber, rays of light are guided along the fiber core by total internal reflection. Rays that meet the core cladding boundary at a high angle greater than the critical angle of their boundary are completely refracted. That critical angle is determined by the difference of index of refraction between the core and the cladding materials. Rays that meet the boundary at a lower angle are reflected from the core into the cladding and do not convey light and hence information along the fiber. The critical angle determines the acceptance angle of the fiber, often reported as a numerical aperture. A high numerical aperture allows the light to propagate down the fiber in rays both close to the axis and at various angles, allowing efficient coupling of light into the fiber. However, this high numerical aperture increases the amount of dispersion as the rays at different angles have different path lengths and therefore take different times to traverse across the fiber. In graded index fiber, The index of reflection in the core decreases continuously between the axis and the cladding. This causes the light rays to bend smoothly as they approach the cladding, rather than reflecting abruptly from the core cladding boundary. The resulting curved paths reduce multipath dispersion because high-angle rays pass more through the lower index periphery of the core rather than the high index center. The index profile is chosen to minimize the difference in axial propagation speeds of the various rays in the fiber. This ideal index profile is very close to a parabolic relationship between the index and the distance from the axis. Single mode fiber or step index fiber. Fiber with a core diameter less than about 10 times the wavelength of propagating light cannot be modeled using geometric optics. Instead, it must be analyzed as an electromagnetic wave structure by the solution of Maxwell equations. As reducing to the electromagnetic wave equations, the electromagnetic analysis may also be required to understand behaviors such as speckle that occur when coherent light propagates in multi-mode, by which the light can propagate along the fiber. Fiber supporting only one mode is called single mode or monomode fiber or step index fiber. The behavior of large core multi-core fiber can also be modeled using the wave equation, which shows that such fiber supports more than one mode of propagation. The result of such modeling of multi-mode fiber approximately agree with the predictions of geometric optics. If the fiber core is large enough to support more than a few models, the waveguide analysis show that the light energy in the fiber do not completely confine in the core. Instead, especially in single-mode fibers, a significant fraction of energy in the boundary mode travels in the cladding as an evanescent wave. The most common type of single-mode fibers have a core diameter of 8 to 10 micrometers and is designed to use in the near-infrared region. The mode structure depends on the wavelength of the light used, so that this fiber actually supports a small number of additional modes at visible wavelengths. Multi-mode fiber, by comparison, is manufactured with core diameter as small as 50 micrometers and as large as hundreds of micrometers. The normalized frequency for this fiber should be less than the first zero of Bessel function, approximately 2.45. Special purpose fibers or step index multimode fibers. Some special purpose optical fiber is constructed with a non-cylindrical core and or cladding layers, usually with an elliptical or rectangular cross section. These including polarization maintaining fiber and fiber designed to suppress whispering gallery mode propagation. Polarization maintaining fiber is a unique type of fiber that is commonly used in fiber optic sensors due to its ability to maintain the polarization of light inserted into it. Photonic crystal fiber is made with a regular pattern of index variation, often in the form of cylindrical holes that run along the length of the fiber. Such fiber uses diffraction effects instead of total internal reflection. Once again, thank you for viewing this video.